But now the electron is gone. Okay, and you have 2 sum over beta. Beta is the number of channel, and this is why it's good to have this example, because now you have 2 channel. So here I would have beta equal from 1 to 2. You can have OG or you can have ICD channel. Okay, and for each of them you have a continuum, and this is your continuum. So that would be, for example, Chi1 would be neon plus plus. And this guy here, that's this electron here. Okay? And for beta equal 2, that would be K beta would be this guy here, and this energy here would be the energy of this electron. Okay? And it's actually a CI. It's a configuration interaction development. Okay? But not in terms of determinants, in terms of states, quasi-bond states, and continuum. Okay? And how do you get your width? It's simple. You get the coupling. So that's the width in energy. All right. So it's 2 pi, the sum over the channel of the coupling between the bond part and the continuum part at the energy of the... Otherwise, like this, that should be enough. Okay? And as I said, you have to sum over the channels, and this is why the width is the sum of this one and this one. If you want the lifetime, you just take the inverse of that. Okay? Sorry, it's the electronic Hamiltonian. Before I call it HE, thanks. Yeah, it's the electronic Hamiltonian, yes. That's the decay rate, yeah. Hmm? You can derive it from the the Fermi-Golden rules, but if you do that, you should have a delta here. But actually, in the Fano derivation, you don't need to use Fermi-Golden rules. Yeah, but I use atomic units. But you're right, there should be a h bar. Yes, h bar is 1. Yeah. As I said, I'm not rigorous. So if there are Burger mistakes and so on, I apologize, but it's again just to give you a feeling. Okay. If you want, if you want more rigorous definition derivation, just let me know. I'll show you the papers and we can go through the papers. Well, there is the paper from Auger in 61, I think. But the one I like is the I have to find the reference, but it's what took this and applied directly to Auger. No, I don't think so. No. Mm-hmm. But there are papers where it's well detailed. So at least how to compute ICD width and so on. Yeah. There is a special issue for lens birthday actually, where there are several papers where it's maybe more detailed and so on. So this can be. And there is a review on ICD also. In Lens, can you help me? Chemical reviews. Yeah, chemical reviews. 2021, I think, or something. Yeah. There is Thiel, Andreas Dreuf, Lenz, Kirill Kochberg. But really all those papers that I mentioned and so on, if you want to see them, just write to me. Maybe I should put my email address. And I'll send it to you. Yeah? Okay, I don't need to? Okay. Yeah. All right. Other questions? Yes. You are, if you want to be correct, you have to sum over the two, yeah. No, no. Beta equal 1, that's here. Beta equal 2, because here it goes NC equal 2, that's this one. So if I include one here, that's only the Auger width. Okay. And if you want the branching ratio, so the probability to go there or there, you have to do this one, for example, the branching ratio for Auger, that would be this term for beta equal 1 divided by the sum of 1 and 2. Yeah? It's clear? Yes. Yes.
What drives I beta to go to this channel pi and star in that Hamiltonian? You should have a laser.
No, because you don't need the laser. They have the same energy. So M star would be the first part, and the chi would be this guy here. Yeah, they have the same energy, and they are coupled by the Hamiltonian. And this comes from your own that. It comes from the fact that you wrote your wave function like this. So you made some kind of partition of your states. Some states that are quasi-bond and some that are continuum. Okay? All good? Okay. So now, that was the Fano theory of resonances in a nutshell. Now, why did I spend an hour explaining the CI method and bother you with quantum chemistry? Because now they enter. Now we need an approximation for the quasi-bond, and we need an approximation for this guy. And those you can compute it with quantum chemistry. So what we do is we do it with CI. Actually, the idea comes from Lenz, where he was using a different method, which is called ADC, that depends on that relies on Green's function. But in our group, we use CI. Okay. So if you remember, okay. We discussed this. So you have your pseudo-continuum, and I told you some of these states are like doubly excited states, and some are continuum. That's what I do. I say, okay, if this one is a doubly excited state, that's my bound part. That's this M star quasi-bound part. And if those guys are the continuum, then that's my continuum, and I complete the coupling between the two. Okay? So those are manipulation. Okay? So this is why you need quantum chemistry. Okay? Something you can see is that I told you the continuum and the quasi-bond part, they should have the same energy, right? Because you need to conserve the energy. If you're here, you cannot go here. Okay? You have to get the same energy. And you see what I drew before? No. Where was it? No. You have to implement it. That's what you have to do. But actually, it boils down to two electron integrals that you can get easily. No, that's not this one. So yeah, I was saying you need to have the same energy, but you can see it what I drew. If this is the quasi-bond part, right? The continuums, they don't have the same energy. Okay? So there is a problem here because you want a continuum that has the same energy as your quasi-bond part, but you don't have it. Okay? And that's the issue of using a finite L-square basis set. This is the thing we discussed if we have to move to infinite functions and so on. So that's an issue. And we need a fix for that. So that's the issue. There are two issues with using CI method here. The first issue is that, well, we have a discrete continuum. Okay, we don't have the continuum at the right energy. And two, this pseudo continuum, they have the wrong boundary condition. They don't look like continuum. Okay, continuum should be normalized to the energy, while the L square they are normalized to 1. So they don't have this proper boundary condition. So that's two issue. Okay, it took longer than I thought. It's good. Well, so I don't know if I should continue. Oh yeah, I'll go quickly then. I want to. Yeah. Yeah. Okay. Well, I'm almost finished, but this part is a bit tricky, so I don't know. Maybe I'll present it, I'll illustrate it, and if there are questions, we'll have time. Okay. So we need a fix for those two problems, and the fix that we use is called the Stiegis imaging method. Okay. So it's just a method to renormalize the pseudo-continuum and to get a pseudo-continuum that you can interpolate at the energy of the bound state. Okay? So how you do it? I'm not going to go into the derivation. I'm just going to tell you the steps that you do. So the first step is that you do CI and you get the energy, you get your pseudo-continuum, you get your quasi-bond state. Okay? Two, you compute your coupling, which I will call F beta for the moment. Okay? You compute your coupling with the wrong continuum state. This K beta can have any energy. It doesn't have to be at the energy. You compute all of them. Okay? So then you get this F beta and you have E beta. And from there, you compute the moments of F beta. So the first moment, second moment, and so on, which is just, so if I call the moment, I will call Mn, right? Is just the sum over all possible beta of F beta E beta to the power of n. Okay? So if n equals 0, you just sum the coupling. N equal 1, you sum the coupling times the energy, and so on. Okay? The idea is that these F beta are not correct because they don't have the right boundary condition, but the moments are correct or a good approximation. They are much better described. They are much closer to the exact moment than this term. And now the idea is that we want to go backward. We want to take this moment and guess what is the right moment, the right coupling. Okay? So we have this inverse problem or reverse engineering kind of to do that, and that's the imaging. So I'm not going to explain how it's done, but that's what you do. You do stages, imaging, and the stages give you back F beta tilde and E beta tilde. So it gives you the energy of the continuum and this coupling here, but now with the right boundary condition. Okay? And this you can use it to interpolate and get your width. Okay? So some quantum chemistry, some Fano theory of resonances, and here some moments. So it's the inverse moment theory. Actually, this is a still ongoing problem. There are mathematicians working on that and trying to find this. So there are other methods than stages imaging, but this is what we use. Okay. Again, it's Lens who initiate this with the final ADC, and I just took the code. We tried other things, but this one works best. There is a bit of cooking, but it works fine. Okay? It's good for you? All right. 2 minutes, and then... okay. Then I will... So no question here because I'm going to change computer and then we won't see the screen. No. Okay. So I have implemented the method in quantum package, and here I show you the CI result. I told you we need the CI states for the bound part and for the continuum part. And this is what you see. This is neon again. Okay. And I make a hole in the 1s orbital. So the bound part is this guy here. He has some energy minus 86.6. And all those things, those are these pseudo-continuum states. And I have really a bunch of them, right? So if you look, I don't remember, I have, about 700 pseudo-continuum states, okay? But they have the wrong energy, okay? So that's what I drew before, okay? But I can compute the coupling between the first guy that I show you and all of them. Then I compute the moments that are from this distribution, and then I do stages to get the right coupling, okay? And just to finish, to illustrate that, so if I compute the coupling from the CI states, I get this, okay? So that's the coupling as a function of the energy. Okay? And my resonance, I always shift things such that the resonance is at 0. So you see that there is no point here, and it's a mess. So if I try to interpolate this, it's hopeless, right? And I would get wrong result anyway. Okay? Now I take this coupling, I go into this stages procedure, again, computing the moments of this distribution of points, and then do the inverse transformation, and then I get... don't remember. So how much is it? It's core. It should be 0.2, but I'm not sure I put the 2 pi. So it could be in EV, but then I don't put the 2 pi. So no, I prefer not to say. Okay, it's just the shape that you should, the value. Uh, yeah, it's really the shape, just to see that you have a crazy distribution. But you can compute the moment from there and then do the inverse. Okay, and then if you do that, you get this. So that's now the same distribution, but corrected by the stages. So again, the coupling and the energy. And again, my resonance, I put it to 0. So now I draw a line, but it's cheating because you actually have points here, 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 but I don't have it at 0 exactly. But now it's well behaved. So then I can do an interpolation and get my coupling here and get my resonance width. So this is how I do it. No. It's just the scale, but it's not 0. It's yeah. If you do so here I don't remember what is it, but if you transform it in width, you get 200 millieV, which is very close to the experiment. Nothing. Those are not important. The only thing that is important is at this point. All right. No. It's really let's say an artifact of. You can see it as an artifact of the method of the CI, because here those are not resonances. Okay, your resonances is at one position. It's always at 0. Yeah, so it goes to 0. Okay. No questions. So everything that I've shown here, they are open source thing. I mean, the quantum package, you can download it, install it, and there is a plugin to do this NOCI method. The documentation is not well done, to be honest. I didn't spend a lot of time doing, but it's there. It's there. So in principle, anyone can use it. So and it's not that difficult to use it. Again, what's important is to get some experience with that and really testing and making sure you understand what's going on. Because quantum chemistry can be easy, but it can be also really misleading. Okay, you cannot just trust the number that goes out. You need to know what they mean. All right, so I'm done. If there are no questions, thanks.